Welcome back to the Deep Dive. Today we're tackling, a fundamental idea about space, that huge expanse between the stars. Most people think of it as just empty.
Yeah, it's the classic picture, isn't it? A void. A perfect vacuum. But, the more we look, especially with things like radio telescopes, the more we realize that space, the interstellar medium, the ISM, it's not empty at all. It's actually incredibly dynamic. Crucial, really.
So that's our focus for this deep dive, the ISM. We're digging into some key source material about its properties, how we even detect it, and why it matters so much. And there's this fascinating side angle too, right, about interstellar communication.
Exactly. The ISM isn't just some passive backdrop. It affects everything. It's the stuff stars are made from. It filters light. It shapes galactic evolution. And yeah, if you think about sending signals across the galaxy, you have to deal with the ISM.
Okay, but here's the bit that immediately grabs me, the paradox you mentioned. It's incredibly sparse, almost nothing there.
Right.
Yet you're saying it behaves like a compressible fluid, not a vacuum. How does that work?
That's the core concept, isn't it? It seems totally counterintuitive, but yeah, scientifically it's a fluid.
All right, let's unpack that. This sounds like the perfect place to start. Section 1, the illusion of vacuum in basic composition. How sparse are we actually talking?
We're talking extremely sparse. If you take a sample near the plane of our galaxy, the average density is something like 1 atom per cubic centimeter.
One single atom.
Yeah.
In a box the size of what, a sugar cube?
Pretty much, yeah. Just one.
Okay, put that into perspective for us. How does that compare to, say, the air we're breathing right now?
Oh, it's not even close. In that same cubic centimeter of air, you've got roughly $2.07 times 1019 molecules. That's 27 million trillion molecules versus 1 atom. The difference is staggering.
Mind-boggling. And even our best lab vacuums.
Even the absolute best ultra-high vacuum chambers we can build on Earth, they still contain maybe 1,000 atoms per cubic centimeter, probably more.
So the ISM is way, way emptier than anything we can create.
Orders of magnitude emptier.
Yes. Okay, so point taken, it's ridiculously sparse. But you still insist it's not a vacuum. Why the distinction? Why does that technical point matter so much?
It boils down to the physics definition of a vacuum, which hinges on something called the mean free path.
Right, I remember that term. That's how far something travels before it bumps into something else.
Exactly. The average distance an atom or molecule travels before colliding with another one. Now, in a lab chamber, if that mean free path is longer than the size of the chamber itself,
Then the particles mostly hit the walls, not each other.
precisely, and that's when you have a true vacuum in the technical sense. Particle interactions are negligible compared to wall interactions.
But in space, the chamber is, well, the space between stars, light years across.
Exactly. Huge distances. And here's the kicker. Even at that incredibly low density of 1 atom per cubic centimeter, the average distance an atom travels before hitting another atom, the mean free path, is actually hundreds of times smaller than the typical distances between stars.
Wait, run that by me again. Even out there, where it's almost empty, the particles are still close enough relative to the vastness of space that they interact with each other more than they just fly off indefinitely.
That's exactly it. It's a difficult scale shift to wrap your head around, I know. But because that mean free path is short compared to the system's dimensions, particles are constantly exchanging energy and momentum. They're interacting.
Ah, so they behave collectively.
Yes. They act as a continuous medium, not just isolated bullets flying through space. And because it's a gas, it's compressible.
Okay, I think I'm getting it. So if it's a continuous compressible medium,
Then the laws of gas dynamics apply. Fluid dynamics, essentially.
and what does that unlock? What can we model once we know that?
Oh, everything. It means the ISM can support waves, like shock waves from supernovae or from stars plowing through the gas.
Like a bow wave from a boat.
Exactly like that. It means pressure differences matter. It means the gas can clump together under gravity, cool down, and eventually collapse to form new stars and planets. Without treating it as a fluid, star formation just doesn't make sense.
And that continuous nature also impacts our communication idea, right? If it were a true vacuum, signals would just zip through.
Right. But a continuous medium, especially if it's ionized in places, can scatter, disperse, or absorb signals. Think about trying to shout through fog versus clear air. The medium itself affects the message. So for any serious thought about interstellar communication, understanding the ISM is step 1.
Gotcha. Okay, so we know how it behaves, like a fluid. What's it actually made of? Is it just leftover stuff from the Big Bang?
Mostly, yes. Its basic chemical makeup is very similar to the outer layers of stars like our sun. It's overwhelmingly hydrogen and helium.
The lightest elements. Makes sense.
About 70–75% hydrogen, 25–28% helium by mass. Everything else, what astronomers lump together and call metals, carbon, oxygen, iron, all that.
It's just a tiny fraction.
Yeah.
Like 1–2%.
Exactly. It reflects the fact that this material hasn't all been processed through multiple generations of stars yet. It's still relatively primordial, enriched slightly by past supernovae.
But it's not just individual atoms floating around. The source mentioned molecules.
Right. It's not purely atomic. We do find simple molecules in noticeable amounts. Things like CO, carbon monoxide, and CN, cyanogen, were detected fairly early on.
And the big one, molecular hydrogen, H2. You said a significant portion is likely in that form.
Yes. H2 is thought to be the most abundant molecule by far, especially in the denser, colder regions. It's the primary fuel for making new stars.
But it was hard to detect directly, wasn't it? Why is that?
The H2 molecule is tricky. It's symmetric, nonpolar. It doesn't have an easy handle for electromagnetic radiation to grab onto, at least not at the common radio or visible wavelengths that get through Earth's atmosphere.
So unlike atomic hydrogen, which we'll get to, H2 is kind of quiet, spectrally invisible from the ground.
Pretty much. For decades, its presence was inferred, predicted by chemistry models of cold clouds, but we couldn't directly see it widespread.
Until we got telescopes above the atmosphere.
Exactly. Space telescopes operating in the far ultraviolet, that was the key. They could finally pick up the specific spectral lines from H2, confirming it's out there in huge quantities, especially in those cold, dark clouds. It really showed us where the densest parts of the ISM are hiding.
Okay, so the ISM isn't uniform. It's got these different zones, different chemistry.
Absolutely. It's a very patchy dynamic environment. Which leads us perfectly into section 2. Hot zones, cold clouds, and cosmic dust.
Right, so the state of the gas depends heavily on nearby stars.
Very much so. Proximity to hot, massive stars makes all the difference. This naturally divides the ISM into basically two main types of regions, HII regions and HAI regions.
HII, that's the hot ionized stuff.
That's right. HII means ionized hydrogen. You find these zones around the most energetic stars, the big blue O and B stars. They pump out enormous amounts of high-energy ultraviolet photons.
And those photons strip the electrons off the hydrogen atoms.
Exactly. They ionize the gas completely, creating these vast bubbles of plasma. We call them Strömgren spheres.
How vast are we talking?
For a really hot star, like a class 05, the ionized region can stretch out for, say, 100 parsecs, maybe even more.
100 parsecs, that's over 300 light years, just from one star.
Yeah, it's an immense volume. That UV radiation totally transforms the surrounding medium over huge distances.
And because it's ionized plasma, it's also hot.
Very hot. Temperatures in HII regions can reach up to 10,000 Kelvin.
And that heat makes them glow.
It does. The electrons recombine with the protons, cascading down energy levels and emitting light. That characteristic red glow you see in pictures of nebulae like Orion, that's mostly the hydrogen alpha line, the signature emission from these hot ionized HII regions.
Okay, so those are the hot bubbles. What about the rest of space, the HI regions?
HI denotes neutral hydrogen, where the electron is still attached to the proton. These are the regions far enough away from those hot stars that the hydrogen stays neutral. This is the bulk of the ISM volume.
And these are much cooler.
Much cooler, yeah. Typical temperatures are down around 100 Kelvin, maybe even colder in the densest parts. Think deep freeze temperatures.
And this is where the molecules hang out.
Exactly. These cold, neutral HI regions, especially the dense cores within them called molecular clouds, are where the chemistry happens. They're shielded from the harsh UV radiation, allowing atoms to link up and form molecules, including that all-important H2, but also CO, water, ammonia, and much more complex stuff.
Let's quickly connect that back to the communication problem. Signals passing through an HII region. That sounds like trouble.
Big trouble. Plasma does messy things to radio waves. It causes dispersion. Different frequencies travel at slightly different speeds, which smears out a signal. It can bend the path, cause scintillation. Basically, it degrades the information content significantly over long paths.
So you'd ideally want a path through the cool HI regions.
Generally, yes. HI regions are much kinder to radio waves in that sense, but they aren't perfectly transparent either. They absorb radiation at specific frequencies, like the 21-centimeter line we'll talk about. The point is, the medium is always a factor. It's never truly empty passage.
Okay. Beyond the gas, hot or cold, there's also dust. Cosmic dust, what is this stuff?
It's tiny, solid particles, think microscopic grains, probably made of things like silicates, basically sand, and carbon compounds, maybe graphite or soot, often coated with ices like water ice or frozen ammonia in the coldest parts.
How tiny are we talking?
Really tiny. Sizes range from maybe 10 to 4 centimeters, smaller than smoke particles.
Individually minuscule, but collectively.
Collectively, they're incredibly effective at blocking light, especially shorter wavelengths like blue and ultraviolet light. This is called interstellar extinction, or reddening.
And this is why we can't see very far when we look along the disk of the Milky Way.
Exactly. The dust acts like a fog. If you look along the galactic plane, the dust builds up and blocks the light from distant stars. Beyond about, say, 2,000 or 3,000 parsecs, the view gets completely obscured in visible light. It limits our ability to map the galaxy optically.
That's a major limitation. But there's a saving grace in its distribution.
Yes, thankfully. Both the gas and the dust are highly concentrated in a relatively thin layer around the galactic midplane. The disk is maybe 100,000 light years across, but only about 250 parsecs thick in terms of where most of this gas and dust lives. Let's say roughly 800 light years thick.
So if we look straight through the plane, we hit that wall of dust quickly.
Right.
But we go slightly up or down out of that plane.
We're looking through much less material. The path length through the dense layer is shorter, so we can see much farther, out to distant galaxies relatively unimpeded. The geometry helps us out.
And how much mass is actually in this dust compared to the gas?
It's a tiny fraction by mass. The overall gas-to-dust ratio by mass density is roughly 100 to 1.
So gas is king in terms of mass.
Overwhelmingly. But the dust, even at 1%, punches way above its weight when it comes to blocking visible light.
Okay, now let's go back to the ISM as this fluid. You said it's not smooth, it's clumpy. What does that mean structurally?
Yeah, clumpy is a good description. It's highly non-uniform. The ISM isn't a smooth, diffuse haze spread evenly everywhere. Instead, most of the gas and dust is concentrated into distinct structures we call interstellar clouds.
So these are regions with higher density than the average.
What higher? Inside a typical cloud, the density might be around 10 atoms per cubic centimeter, maybe more, compared to the average of 1. And in the really dense cores where stars form, it can get much, much higher still.
So you have these denser clouds separated by, what, near emptiness?
Pretty much, yeah. Vast regions of much hotter, much lower density gas in between the cooler, denser clouds. It's a very frothy, filamentary structure overall.
And where do we find these clouds mainly?
They tend to congregate in the spiral arms of the galaxy. That's where the action is, where the compression happens. And these clouds aren't static. They move with the galaxy's rotation, but they also have their own random turbulent motions on top of that.
How fast are they moving individually?
Their peculiar velocities, the sort of random jostling around, are typically around 6 to 8 kilometers per second. Not super fast on a galactic scale, but enough to make the ISM a very dynamic place.
And when we see those amazing pictures of dark nebulae, like the Horsehead Nebula or Bright Emission Nebulae, those are these clouds.
Those are the most prominent examples, yes. The densest clouds become visible either as dark silhouettes against background stars, dark nebulae because they block the light, or they glow brightly if they happen to be near a hot star that illuminates them. Bright nebulae like HII regions or reflection nebulae. So this clumpy, cloudy structure is fundamental to how the galaxy looks and operates. It's where stars are born.
Okay, this paints a much more complex picture than just empty space.
Yeah.
But if the dust blocks our view, how did we figure all this out? How did we measure the motion, the temperature, the sheer amount of this invisible gas?
Well, that's where radio astronomy came in and truly revolutionized everything. It gave us the tools to see through the dust.
Right. Which brings us to section 3. Radio astronomy peering into the ISM's depths. And the cornerstone was this 21-centimeter line.
The 21-centimeter line of neutral hydrogen, the HI line. Absolutely fundamental. It was predicted theoretically back in the 1940s based purely on quantum mechanics, long before we could actually detect it.
And it's a different kind of process than normal light emission from electron shell jumps.
Totally different, much more subtle. It happens within the ground state, the lowest energy state of a single neutral hydrogen atom. That ground state isn't quite single. It's split into 2 very closely spaced energy levels.
And the difference is about spin.
Exactly. It's about the relative orientation of the intrinsic magnetic moments, the spins of the proton nucleus and the orbiting electron. They can either be aligned parallel spins, which is a slightly higher energy state, or anti-aligned, anti-parallel spins, the slightly lower energy state.
So the atom can flip from the higher state to the lower state.
Yes, spontaneously. And when it does that spin flip, it has to release that tiny little bit of energy difference as a photon.
And because the energy difference is so minuscule,
The photon has a very low energy, which means a very low frequency and a very long wavelength. And that wavelength turns out to be almost exactly 21.1 centimeters. That corresponds to a frequency of 1420 megahertz, right in the radio part of the spectrum.
okay, simple enough quantum leap. But you said it was rare.
Astonishingly rare. For a single isolated hydrogen atom, the average time it would take to spontaneously make this spin flip transition is about 11 million years.
11 million years for one atom to emit one photon.
Yep. Compare that to a typical optical transition in electron jumping shells, which happens in about 100 millionth of a second. This 21 centimeter transition is incredibly forbidden, quantum mechanically speaking. It almost never happens.
So if it's that rare for one atom, how on earth do we detect it from light years away? It sounds impossibly faint.
It would be impossibly faint, except for one thing. The sheer mind-boggling number of hydrogen atoms out there.
Ah, the volume of space compensates for the rarity.
Exactly. Even at 1 atom per cubic centimeter, when you look along a path through the galaxy that's thousands of light years long, you're looking through an absolutely colossal number of neutral hydrogen atoms. So even though each one only emits a 21 centimeter photon once every 11 million years on average, there are so many atoms doing it at any given moment that the combined signal is actually strong enough for our large radio telescopes to pick up.
The universe makes the improbable observable through sheer scale. That's amazing.
It really is. It's a beautiful example of it.
So what did observing this faint radio hum allow astronomers to do?
It was revolutionary. Suddenly, we could map the neutral hydrogen gas throughout the entire Milky Way, even on the far side, because radio waves cut right through the dust that blinds optical telescopes.
And it tells us more than just where the hydrogen is, right? You mentioned dynamics.
Oh, absolutely. The key is the Doppler effect. The hydrogen gas clouds aren't stationary, they're moving. Some are moving towards us, some away as part of the galaxy's rotation, and also due to their own random motions.
And that motion shifts the frequency of the 21 centimeter line.
Precisely. If a cloud is moving towards us, we detect the line at a slightly higher frequency, shorter wavelength. If it's moving away, we see it at a lower frequency, longer wavelength.
So the single frequency gets smeared out into a profile.
Exactly. We observe a line profile intensity plotted against frequency. And by analyzing the shape and shifts of that profile from different directions in the sky, we could piece together the rotation curve of our galaxy, map the spiral arms, measure the speeds of individual clouds, that 6 to 8 kilometers turbulence we talked about. We could even estimate the temperature of the gas from the width of the line. It was like turning on the lights in a dark room.
A complete game changer for galactic structure.
Totally. And we could apply the same technique to other nearby galaxies like Andromeda and map their hydrogen gas and rotation too.
Okay, so 21 centimeter gave us the atomic hydrogen map. But you also said a lot of the gas, especially in cold clouds, is molecular hydrogen, H2. Did radio astronomy help find the molecules too?
It certainly did. Following the success of the HI line, the next big wave of discoveries in the 1960s and 70s came from detecting radio lines from molecules. This confirmed that yes, in those cold, dark clouds, the gas is predominantly molecular.
What were some of the first molecules detected this way?
One of the really important early ones was the hydroxyl radical, OH. It has lines around 18 centimeter wavelength. And interestingly, its presence in the ISM was actually predicted, theoretically, way back in 1949 by Yusuf Shklovsky, whose work informs some of our source material today.
The same Shklovsky. Wow. Took a while for observations to catch up.
It did. It was finally detected in 1963. And the OH line isn't simple either. It's actually split into 4 closely spaced components due to its structure.
Okay, what came after OH?
Water, H2O, was a big one, found in 1967 via its line at 1.35 centimeters. Ammonia, NH3, was found shortly after. And discovering these lines, particularly OH and H2O, led to something else really unexpected.
Which was?
Cosmic masers. intense, amplified microwave emission. It turns out that under the specific conditions in some dense molecular clouds, the populations of energy levels for molecules like OH and H2O can get inverted, leading to natural maser action like a laser, but at microwave frequencies.
Nature inventing the laser before we did. That's wild.
It is pretty amazing, found completely by accident while studying these molecular lines.
But I've heard that carbon monoxide, CO, is really the key molecule for mapping these days.
Yes, CO has become the workhorse tracer for molecular gas. It has a strong emission line at a wavelength of 2.6 millimeters. Because H2 itself is so hard to see directly at radio wavelengths, and CO seems to exist wherever H2 is abundant and is much easier to detect, astronomers use CO emission as a proxy to map the location, mass, and structure of those vast molecular clouds where stars are born.
So follow the CO, find the H2.
Pretty much. It's observed almost everywhere we find molecular gas.
And the discoveries didn't stop at simple molecules like CO, OH, and water.
Not at all. That was just the beginning. Once the techniques were refined, there was an explosion of discoveries. Within a fairly short time, over 50 different types of molecules were identified in the ISM.
And today?
Today, the count is well over 200 distinct molecular species identified in interstellar or circumstellar environments. And some of them are surprisingly complex.
How complex are we talking?
We're finding molecules with chains of carbon atoms, ring structures, things like ethyl alcohol, acetic acid, even glycolaldehyde, which is a simple sugar. Molecules with up to 13 atoms, maybe more now. Things like methylformate, CH3HCO, and methylcyanide, CH3CN, were found in dense, cold clouds.
Wait, alcohol, sugar, in interstellar clouds.
Yep. Simple versions, but yes. The chemistry happening out there in those cold, dark conditions is far richer and more complex than anyone initially imagined.
That immediately makes you think about the origin of life, doesn't it? If space is cooking up this kind of organic complexity on its own.
It's the driving question for astrochemistry and astrobiology, absolutely. Finding these complex organic molecules proves that the pathways to biological precursors can operate in space. Now, we need to be clear. We haven't found things like amino acids, the building blocks of proteins, or DNA or RNA directly in the ISM yet. The search is ongoing, but the evidence points towards space being a potential source for the chemical ingredients needed to kickstart life on young planets.
So the seeds of life could be widespread.
The chemical seeds, yes. That seems increasingly likely.
There was another cool application mentioned in the source using isotopes, observing different versions of these molecules.
Yes. Isotopic analysis. That's a really powerful tool. See, an atom is defined by its protons, but it can have different numbers of neutrons. Those are isotopes, like carbon-12, the common form, and carbon-13, rarer, with an extra neutron.
Okay.
When these different isotopes get incorporated into a molecule, say CO, you get tex-texto or even texto using a heavier oxygen isotope, because these molecules have slightly different masses.
Their energy levels are slightly different.
Exactly, which means their spectral lines, the radio frequencies they emit or absorb, are slightly different too, measurably different.
So by carefully tuning your radio telescope, you can distinguish between CO made with carbon-12 and CO made with carbon-13.
Precisely.
Mm-hmm.
And by measuring the relative strength of these different lines, you can figure out the abundance ratio of the isotopes, like the ratio of carbon-13 to carbon-12 in that particular cloud.
Why is that useful? What does that tell us?
It tells us about the history of the material. Stars fuse lighter elements into heavier ones, and different types of stars and processes produce different mixes of isotopes. So the isotopic ratios in the ISM act like fingerprints, revealing how much the gas has been processed through previous generations of stars, how much supernova debris has been mixed in. It's a crucial tool for understanding the chemical evolution of the galaxy over billions of years.
Wow. Reading the galaxy's history and isotope ratios. Okay, one more radio technique before we move on recombination lines. These are for the hot HII regions.
Yes, radio recombination lines offer another window into those hot ionized HII regions. This method was actually predicted by the Soviet astronomer Enis Kardashev, another name heavily involved in the search for extraterrestrial communication, interestingly enough.
What are these lines? How do they work?
They come from electrons recombining with protons, but specifically involve transitions between very highly excited energy levels of the hydrogen atom.
Right.
We're talking about electrons jumping between levels like N108 and N107, or N200 and N199, really huge quantum numbers.
Levels 108 and 107. I thought atoms only had a few energy levels.
In normal conditions, yes, the outer electrons are easily stripped off or perturbed. but the ISM is so incredibly tenuous, the density is so low.
That these ridiculously delicate, highly excited states can actually exist for long enough to radiate.
That's exactly it. In the dense atmosphere of the sun, for instance, interactions with surrounding particles disrupt any hydrogen atom excited beyond about the N28 level. But in the near vacuum of an HII region, these right atoms with electrons way out in the boondocks can survive. The transitions between these high-end levels release very low-energy photons, which fall in the radio part of the spectrum.
So the very existence of these lines is proof of the extreme low density.
It's a beautiful confirmation. And observing these lines gives us another way to measure the temperature, density, and motion of the plasma in HII regions, complementing optical observations.
The ISM's emptiness enables unique physics. Okay, let's shift gears. This fluid, this gas and dust, isn't just floating freely. Section 4. Magnetic fields, cosmic rays, and evolution. There's magnetism out there.
Oh, yes. A pervasive, weak, but incredibly important interstellar magnetic field. Its existence was inferred indirectly for quite a while from things like starlight polarization, but nailing it down directly was tough.
And this field is tied to the gas.
Yes, the field lines are essentially frozen into the plasma component of the ISM. Where the gas goes, the field lines generally follow, and vice versa. They move together.
How strong is this field?
It's incredibly weak by everyday standards. The average strength is about a few microgas, or 10.5 or Ørsted in the units used in the source.
How weak is that compared to, say, Earth's magnetic field?
Earth's surface field is about half a gas, so the interstellar field is roughly 100,000 times weaker. Tiny.
Yet you say it's important.
Crucial. Because it extends over such vast distances, it exerts a significant influence. Think of it like tiny threads making up a strong rope when woven together over light years.
And does it have a structure, a direction?
It does seem to have a large-scale structure. The general direction of the field seems to align roughly with the spiral arms of the galaxy.
So the spiral arms are like magnetic tubes.
That's a good way to think about it, yeah. Giant magnetic flex tubes that help organize the gas flow and potentially even trigger star formation within the arms.
How did astronomers finally measure such a weak field directly? That sounds incredibly difficult.
It was a triumph of radio astronomy in the early 1960s. English astronomers used the Zeeman effect on the 21-centimeter line.
The Zeeman effect.
Yeah.
That's where a magnetic field splits a spectral line into multiple components.
Exactly. The magnetic field slightly alters the energy levels involved in the 21-centimeter spin flip transition, causing a very slight splitting of the line frequency.
But if the field is 100,000 times weaker than Earth's, that splitting must be minuscule. How could they possibly see it, especially with the line already broadened by the gas motion?
They couldn't see the splitting directly, it's far too small. But the Zeeman effect also causes the different split components to have slightly different polarizations, circular polarization specifically. They used strong background radio sources, like the Crab Nebula supernova remnant, and looked at the 21-centimeter line in absorption as the ISM gas passed in front of it.
Okay.
By making extremely precise measurements of the polarization across the width of the absorption line profile, they could detect the very subtle systematic polarization differences predicted by the Zeeman effect for a field of a few microgauss. It was an incredibly delicate observation.
Wow. Pulling that tiny signal out of the noise. Is there another way to measure it? The source mentioned the Faraday effect.
Yes, Faraday rotation is another key technique, perhaps more widely used now for mapping the large-scale field. It works on polarized radio waves coming from distant sources, like pulsars or quasars outside our galaxy.
How does that work?
As that polarized radio wave travels through the magnetized plasma of the ISM, its plane of polarization gets rotated. The amount of rotation depends on the strength of the magnetic field along the line of sight, the density of electrons, and the distance traveled.
So by measuring the rotation from many different sources in different directions,
You can build up a 3D map of the magnetic field structure throughout the galaxy. Pulsars are particularly good for this because their signals are often highly polarized.
okay, so we have this weak but pervasive magnetic field shaping the galaxy. What's its main role in things like star formation?
It plays a really critical, maybe even decisive role. As a gas cloud starts to collapse under its own gravity to form stars, the magnetic field embedded within it resists that collapse.
Magnetic pressure.
Sort of. It resists compression perpendicular to the field lines more than parallel to them. It acts like a support, slowing down the collapse, allowing the cloud to radiate away heat more effectively. It also helps channel the collapsing gas along the field lines, potentially shaping the resulting protostellar disks and jets. It prevents a simple, chaotic, free-fall collapse.
So no magnetic field, maybe very different kinds of stars or fewer stars?
Quite possibly. The efficiency and mode of star formation would likely be very different without interstellar magnetic fields.
Okay, now intertwined with the magnetic fields are cosmic rays. What are these exactly?
Primary cosmic rays are high-energy charged particles flying through space. Mostly protons, hydrogen nuclei, but also helium nuclei, electrons, and nuclei of heavier elements, all stripped bare.
And they have incredible energies.
A huge range of energies. From millions of electron volts, maybe up to staggering energies like 10 electron volts, that's the energy of a well-served tennis ball packed into a single subatomic particle. Where the highest energy ones come from is still a bit of a mystery.
And how do they interact with the magnetic fields?
Because they're charged particles, their paths are bent by the interstellar magnetic field. They spiral around the field lines, gyrating along them like beads on a wire, effectively trapped within the galaxy for long periods.
And this movement creates radio waves.
The electron component of the cosmic rays does, yes. When high-energy electrons spiral around magnetic field lines, they emit electromagnetic radiation called synchrotron radiation.
Ah, so that's where the general background radio noise from the galaxy comes from?
A large part of it, yes. The diffuse synchrotron emission we detect across the sky is the combined glow of countless cosmic ray electrons spiraling in the galaxy's magnetic field. So radio astronomy doesn't just study the gas, it also lets us study the cosmic rays and magnetic fields permeating the ISM. It gives us handles on their origin, which is often tied to supernova remnants, the explosions of massive stars.
Okay, this brings us back to that profound connection mentioned earlier, cosmic rays and the evolution of life.
Right. This is where galactic astrophysics touches on astrobiology. The background level of high-energy radiation in space, which is dominated by these cosmic rays, is thought to be a significant factor in evolution.
How so? By causing mutations.
Exactly. High-energy particles can damage DNA, leading to mutations. Some level of mutation is necessary for evolution to occur, providing the raw material for natural selection. But the rate matters.
And the source material suggests...
What?
That the rate could vary.
It poses a hypothetical. What if the cosmic ray flux, the amount of radiation hitting a planet, was much higher, say dozens of times higher than what Earth experiences? The mutation rate might become overwhelming, life might struggle to maintain stable genomes, or it might be forced into highly shielded environments like deep underground or underwater. The path of evolution could have been completely different.
So the relative stability of the cosmic ray environment might be another habitable zone requirement, alongside liquid water and temperature.
It could well be. Which leads to a really deep question. Has the cosmic ray level remained relatively stable on planets like Earth over the hundreds of even billions of years needed for complex life to arise and evolve? What keeps it stable? Is it just luck? Or are there galactic-scale regulatory mechanisms we don't fully understand?
That's a huge question. The ISM isn't just background. It's potentially regulating the conditions for life itself.
The state of the ISM, the fields, the radiation... It all seems interconnected with whether life like us can even get started and persist.
Let's zoom out then for our last section, Section 5. The ISM in the galactic context. We know what it is, how we see it, its forces.
Yeah.
But how much stuff are we talking about overall?
In terms of mass, the total amount of interstellar gas, mostly hydrogen and helium in our Milky Way galaxy, is estimated to be around 1 billion times the mass of our sun.
1 billion solar masses. That sounds like a lot.
It is in absolute terms, but compared to the total mass of the galaxy, it's actually quite small.
What percentage are we talking?
The total mass of the Milky Way, dominated by stars and especially dark matter, is maybe 100 times larger or more. So the interstellar gas makes up only about 1%, maybe a bit more, of the total galactic mass.
So stars and dark matter provide the gravity, but the gas is the active dynamic component.
That's a good way to put it. The gas is the fuel for new stars and the medium through which galactic weather, like supernova shockwaves, propagates. It's the visible, active part of the cycle, even if it's not the bulk of the mass.
And does this gas fraction change depending on the type of galaxy?
Drastically. And that's a key clue to galactic evolution.
How so? Give us examples.
If you look at big old elliptical galaxies, the smooth, reddish, featureless ones, they have very, very little interstellar gas left. Their gas fraction might be down to 10 to 4, 1 part in 10,000 of their total mass, or even less.
And what does that imply?
It implies they've basically used up all their gas-forming stars long ago. They're red and dead, as astronomers sometimes say. Star formation has largely ceased. They're mature, quiescent systems.
Okay, so low gas means old and inactive. What about the other end of the spectrum?
Look at irregular galaxies, like the Magellanic Clouds, our nearby satellite galaxies. They often look messy, actively forming stars in bright blue knots. And sure enough, their gas content is much higher. It can be up to 20%, or in some cases, maybe even 50% of their total mass.
So lots of gas means lots of ongoing star formation, a younger or less evolved system in that sense.
Exactly. The amount of ISM is a direct indicator of a galaxy's current evolutionary state and its potential for future star formation. It connects the small-scale physics of the ISM directly to the large-scale life cycle of entire galaxies.
That really ties it all together.
Yeah.
Okay, this has been an incredibly detailed journey through what most people just call empty space. Let's try to recap the key points.
We started by challenging that idea of empty. We learned the ISM, despite being incredibly sparse, just one atom per cubic centimeter on average, acts like a continuous compressible fluid because the distances involved are so vast.
Right, not a vacuum. Then we saw its complex structure, these giant, hot, ionized HI bubbles carved out by massive stars, contrasted with the vast, cold, neutral HI regions and the even denser molecular clouds hidden within them. That's where the chemistry happens, forming not just H2, but surprisingly complex organic molecules.
And the key to seeing all this, especially through the obscuring dust concentrated in the galactic plane, was radio astronomy. That incredibly rare 21-centimeter spin-flip transition of neutral hydrogen let us map the invisible gas and its motion, revealing the galaxy's structure and dynamics. And radio lines from molecules like CO allow us to trace the fuel for star formation.
We also learned about the other invisible components, the weak but crucial interstellar magnetic field, which guides the gas and helps regulate star formation, detected through subtle effects like Zeeman splitting and Faraday rotation.
And finally, the high-energy cosmic rays spiraling along those magnetic field lines, creating synchrotron radiation and potentially playing a critical role in the mutation rates that drive biological evolution on any planets within the galaxy.
So for you, the listener, the takeaway is that this empty space is anything but. Understanding the interstellar medium, its density, temperature, composition, structure, magnetic field, radiation, it's fundamental. It's the key to unlocking how stars form, how galaxies are structured, how matter evolves chemically, and maybe even understanding the conditions necessary for life to arise and survive over cosmic timescales.
Which brings us to that final provocative thought, stemming directly from the source material's connection between cosmic rays and life. We know cosmic rays influence mutation rates. Life seems to need a relatively stable radiation environment over hundreds of millions of years to develop complexity. So the question is, what ensures that stability?
Is it something about the galaxy's magnetic field structure? Does our solar system just happen to be lucky in its path through the ISM, avoiding denser regions or nearby supernovae? Are there feedback loops involving star formation itself that regulate the cosmic ray intensity over long periods?
We have a snapshot of the ISM now, but its history, its long-term stability, especially regarding the radiation environment it creates. That's a really deep and crucial question for understanding our place in the cosmos and the potential for life elsewhere. How consistent has this interstellar weather been over eons?
The history of the invisible medium, perhaps the most important story, still waiting to be fully read. Definitely something to think about. That seems like a perfect place to leave it for this deep dive. Thank you for joining us.